Section 4.3, Special Cases, Doubling Time and Half-Life. In this section, we're going to solve problems involving doubling time, where they'll tell you something is doubling in maybe so many hours, days, weeks, years, or whatever, and you'll be doing something based on that information. And then the other is half-life. So this will be situations where the amount is becoming half of what it was after a certain amount of time. And we'll approach these problems from some different ways as we go through the section, but they'll all involve either doubling time or half-life. So they are special cases of the exponential growth model we just looked at in 4.2. So for doubling time, if D is the doubling time of a quantity, the amount of time it takes the quantity to double, and P naught is the initial amount of the quantity, just like it's been up till this point, then the amount of the quantity present after T units of time is P of T equals P naught times 2 raised to the T over D power. So why 2? Why do we have the 2 there? Well, if you're doubling, then the growth rate is R equals 1, and P naught times 1 plus R to the T would become P naught times 1 plus 1 to the T, which is just equal to P naught times 2 to the T. So it should make sense. If you're doubling, you're going to see things being multiplied by 2. And that's really what's happening here. So then why the T over the D? Why do we have that extra thing in the exponent now? Well, you need to find the number of times the quantity doubled during the given time. So for example, if the time to double is 4 days and you have gone 12 days, then the amount of doubling periods would be 12 divided by 4, which equals 3. So the power would just be 3. And that's very important because this formula with the 2 in there is saying, hey, we're going to double, we're going to multiply it by 2. And if you just plugged in 12, then it will think, well, it doesn't think because it's just a formula, but it would act and give you a result that was basically indicating that you had doubled 12 times. But that didn't really help it in 12 days because it takes 4 days for each doubling period. So you really only doubled 3 times, and that's why you only want that power of 2 to be 3. So that's why they divide by that D in order to adjust the time so that you know the doubling periods, how many times you should be, essentially multiplying by 2. So first example here, the doubling time of a population of rabbits is 6 months. Suppose there are initially 18 rabbits. Part A, what is the size of the population after T months? So they just want some general formula for this, and with this, we don't have to write the whole P of T. One thing I've noticed with the derivatives, unless they say write an equation for this, they usually just want the right side of that form. So let's go back up in here and get some information. So doubling time is 6 months, so D will equal 6. 18 rabbits initially, that's the P naught. That's the only 2 pieces of information I really have. So we would have 18, the P naught, times 2 raised to the T over 6 power. And that's all they're looking for here in that part A. If it was said write an equation that models this, then we'd have P of T equals. But we don't have that, so just write this. And be careful with derivative. They're not always consistent, so they might ask for that or they may not. But in the ones I've seen, if they don't ask for an equation, then you just have to put the right side. So I apologize in advance for any frustration that you might run into with that. So what is the size of the population after 13 months? Well, now we're going to go ahead and find P of 13. So, this T here is going to be 13. So we're going to have 18 times 2 raised to the, put parentheses around the power, 13 for T divided by 6. And in Desmos, I want to show you how to type this in because If you don't put parentheses around the power, especially in a TI, it's going to give you the wrong answer all day long. So let's go ahead and take a look real quick at this in Desmos. So we'll just type in 18 times 2, and then you do Shift 6 to get to the power, and then parentheses 13 divided by 6, and then a little right arrow to get out of there, and then that. So Desmos is a lot more user-friendly in that you probably didn't need to put parentheses to get this to stay in the power, but the TI doesn't have that feature. So the TI calculators, many times, especially the ones that are not graphing, it would do like 18 times 2 to the 13th power. So, do something like this if you don't put parentheses. Oops. You raise it to the 13th power, and then it'll just do divided by 6, which you can see is a totally different answer. And this is what the TI will do if you don't put parentheses around the power. So be real careful with that. I can't stress that enough. I see students get that wrong all the time because, the calculator's thinking this and you want this. So let's get that out of there. I don't want to see that anymore. So it looks like we got 80.82 roughly, and that will mean that if we round to the nearest rabbit, we'd have approximately 81 rabbits. All right. So that's about it for that type there, and let's go ahead and move into half-life. So half-life, also a special case of the exponential growth model. But in this case, we're going to see the quantity decrease to half of what it was to begin with over a certain time. So this is commonly used with radioactive decay, drug potencies. If you're in the nursing field or all in the medical field, they'll sometimes say, things like, how much drug do you need to make sure that you are keeping a consistent amount over a certain time? If somebody needs to have a certain amount in their system for a treatment, you got to do these calculations because the body is going to metabolize it. It's going to pass it out. And you got to make sure that, you don't get below a certain level and you don't want to have too much. So there's calculations that are related to this that allow you to figure out, how much you need to be giving a person to maintain a certain amount. Or maybe you just want to know, when will they get it all out of their system? And, this half-life is used for those sorts of situations, or at least can be. And radioactive decay is another classic example of half-life. So in the half-life model, if H is the half-life of a quantity, the amount of time it takes the quantity to be cut in half, and P naught, again, the initial amount, then the amount of the quantity present after T units of time is P of T equals P naught times 1/2 to the T over H. So very similar to the doubling, it's just here instead of doubling, you're now halving. So you got a half in there. So why the half? Well, if you think about the R equal to a negative 1/2, negative for decay, then the P naught times 1 plus R to the T would really be equal to the P naught times 1 minus 1/2 to the T, or P naught times 1/2 to the T. And then that T over H, very similar to what was going on with the half-life. Or doubling time, sorry. So with doubling time, we needed to know the actual amount of doublings that happen in a certain amount of time. Well, here the half-life's the same way. You might have a half-life of 10 days, but you're going out 40 days. Well, you're not going to have 40 times. You're only going to have 40 divided by 10, or 4 times. So it's just a way to let you know how many actual times you have halved as you move through the time period based on the actual time it takes to be cut in half. So that's a very common thing with these. You see that fractional power, doubling time, half time, they all use it. So let's go ahead and take a look at an example. So titanium-44 has a half-life of 63 years. If there are 560 grams of this isotope, how much is left after 500 years? Well, half-life here, they give me the H, 50 or 560 grams, so that's going to be the P naught. How much is left after 500? That's the T. Well, I just got to plug that information in. So the P of 500 is going to be equal to 560 times 1/2 raised to the 500 divided by 63 power. So you're just putting all that information into the formula. And when you do that, you're going to get, and this is another one where you really want to be careful with parentheses when you're in this in a calculator, because if you don't, you will get the wrong answer probably every single time. And when you work this out, you get like 2.29 after rounding, so 2.29 grams. And that would be the answer for that one. Let you look at that. All right, so then example 3. This one, got a patient takes 1,000 milligrams tablet of a drug for a treatment at noon. At 9 p.m., there's still 250 milligrams of the drug in their system. What is the half-life of the drug? So what they're really telling me here is the initial amount. They're telling me at noon and then at 9. So they're kind of telling me that T equals 9 here, where this 250 is happening. So this is really the amount at 9 hours later. So what's the half-life? So the H is what we're solving for here. So this is another type of problem. We're going to be solving for a power. We're going to use a logarithm just like we did before, but there's one extra little twist because of the way that the power is a fraction. So let's go ahead and see this. So P of 9 would equal 1,000 times 1/2 raised to the 9 over H. So that's just using the information in the formula. And now I know P of 9 was 250, so I'm just going to put that there. And then again, we need to get this 1/2 with that 9 over H alone so that I can solve for the power using logarithms. This is another place where the logarithms come in. So you get 250 divided by 1,000. After you divide both sides by 1,000, that's 1/2 to the 9 over H. 250 over 1,000 is 1 over 4. I'm just going to break that down. And now at this point, I can go ahead and use the logarithm. So I've got the rate piece alone. So I'm going to put the log of 1/4 equals the log of 1/2 raised to the 9 over H power. And then the whole reason we use logarithms in this class, the only reason we use logarithms, is so I can move powers with variables to the front as a multiplication, as a product. It's a log rule that you would see in algebra. It's the most useful log rule in my opinion, especially for stuff like this. So now at this point, you got an H in the denominator, and there's a few ways you could approach this problem from here, but what I would recommend is just multiply both sides by H. And the reason we're going to do that, if I multiply this side by H and this side by H, the H's on the right side will cancel, and I will now be able to have H times log of 1/4, which will allow me to just divide by the log of 1/4 to get to an answer. So it's just a way of getting that out of the denominator. And H will then equal the 9 log of 1/2 divided by the log of 1/4. And you just put that into Desmos, and 9 times that log of 1/2 divided by the log of 1/4, and you get exactly 4.5 hours. So logs, again, very useful. Make sure that if you're ever solving for a power in an exponential that you're going to use a log on both sides to get that power down so that you can work with it. And that's pretty much what you're going to be expected to do in these sections. So if you have questions, please ask, and I hope you have a great day.